Now that we have seen various approaches to examine data, let us start with sampling exercise. Using the probability sampling techniques, we'll carry out the following analysis with our tool. First, we'll try to understand various approaches to sampling and their implementation in R. Broadly, there are two kinds of approaches: probability sampling approaches, which include simple random sampling, systematic sampling, stratified sampling, and cluster sampling. For empirical studies, these approaches are important. In addition, there are non-probability sampling approaches such as judgment sampling, convenience sampling, and snowball sampling. From empirical analysis perspective, these approaches hold less importance. Therefore, we'll explain and implement the probability sampling techniques, namely probability sampling, systematic sampling, stratified sampling, cluster sampling, and random sampling. We'll start by summarizing the pre and post samples. Next, we'll compute various measures of central tendency. These include mean, median, mode, and quantiles. Then we'll compute measures of range and dispersion. These include range, variance, standard deviation, and mean absolute deviation. Next, we'll visualize the density distribution of pre and post samples and compare them with each other. We'll also compare the pre and post sample density distributions with normal distributions, having mean and standard deviation that is same as pre and post sample distributions. Now that we have discussed the summary and visualization of the data, we'll move to the sampling aspect. We'll discuss a number of sampling techniques. As a part of inferential statistics, we analyze and interpret data. In the previous videos, we discussed and computed various summary statistics, descriptive statistics for the Zio limited case study. In this video, we'll discuss sampling and its different types. A population contains all the items or individuals of interest that one seeks to study. A sample contains only a portion of population of interest. One analyzes a sample to estimate the characteristic when we choose a sample. We want it to be as similar as possible to population. There are many ways to collect a sample. Now we'll discuss the sampling techniques one by one. Predominantly, there are two sampling techniques. One is probability sampling and there's one non-probability sampling. From empirical perspective, probability sampling is the one important. We'll discuss a little bit non-probability sampling, but it remains less important to the empirical aspects. In probability sampling, you have simple random sampling, systematic sampling, stratified sampling, and cluster sampling. For this particular case study, simple random sampling remains the most important, as we will see. Let's start with the very basic simple random sampling. We'll use this sample command. It's provided in base R data functions. I'll apply it on my pre-data to extract a sample of pre-variable. I'll tell it that I need 50 observations from the overall 1000 observations. And I'll also give a command replace equal to t, which tells R that it should be done with replacement. That means the observation taken in the first sampling should be replaced back in the original data. Now, one way to do this is to simply run this command, and you would notice that certain output has appeared on my console. I can run this command again and you would notice a different number of variables on my output. This has happened because every time you extract the random sample, R changes the sample. So one way to do that is to run this command called set.seed and establish a seed number. Let's say set.seed as 51. Once I do that, and if I run, notice that if I run the sample command, notice a certain set of sample has appeared. If I have run the set.seed command, I have fixed it. So every time I run set.seed at 51, you notice same sample is appearing, which is needed to generate the same sample. Now probably a different and more relevant way in this context is to use a variable named pre and assign the sample generated to this pre variable. I run this command where I assign the sample to my pre variable. Similarly, I run a very similar command to assign the post variable sample. So now I'm assigning the sampled values to my pre and post variable, and they are ready for further analysis. For example, I can start with the basic summary operations. I can summarize the data. How? I can use simple summary commands to summarize pre-sample. Notice the minimum, maximum, median, and other inferential statistics. And also notice when I run it on post, the measures of central tendency are appearing, and we can compare the summary of pre-sample as well as post-sample. Now please notice there is a clear shift in the pre-sample versus post-sample, and more importantly, please notice here, using the sample, not the entire 1,000 observations but just a small sample from it, I also reached the same conclusion. So that shows the importance of samples in making inferences about the original data. We will also check the mode of this data as we did earlier. For that, we need that library statip that we earlier installed. We'll use that library statip, and now we'll see some of the initial most frequent observations or that are part of its mode for pre-variable. Let us see some of the initial observations. Similarly, we will use the post variable for its most frequent observations. Please note that in console once I run this command. Clearly, there is a shift in most frequent observations from pre to post. That indicates that there is indeed some impact of training. Next, we can see some of the other measures of central tendency and range as we have seen. So for example, we can look at the quantile measure. So start with quantile command. I can run the quantile command on my pre variable, and I can see this for 20 percentile intervals. With this sequence, I can specify to R that starting from 0 to 1, a 20% percentile interval is to be produced. I can do the same for my post variable also, as you will notice here. And please notice all these measures on sample are indicating a shift. I repeat, a shift on the original data. So that is interesting because we are able to make these inferences using our small sample of 50 observations. So now that we have discussed summarizing and computing measures of central tendency for our sample of 50 observations, which we extracted using simple random sampling, we'll move towards more measures of range and variability after this. Now that we have understood extracting random sample from the data, and we have also seen how to compute measures of central tendency for this data, we'll start with computing measures of range and visualizing the data. So we'll start with computing range measures and measures of dispersion. So for range measure, a very simple formula, range, can be applied to the pre-variable as well as the post variable. We can clearly see the pre and post samples. There is a difference. The range of pre for both lower and higher values is on the lower side. That means the range has shifted after the training and development program, which suggests that there is some significant impact of training and development on employee satisfaction. We'll also check the variance of pre-sample and variance of post-sample. The variance of pre and post-sample are similar. We can also compare the standard deviation of pre-sample and standard deviation of post-sample. They appear to be also quite similar. If you remember, the population measures or the data, when we are referring to population, we mean to say data only. So the data, these measures were quite similar. That means the inferences that we are drawing using the sample are quite similar to the ones we drew when we were working on the original data or the population. That means inferences drawn from samples may give some indication about the nature of original data. We can also compute mean absolute deviation, that is a MAD measure for pre, and mean absolute deviation, that is MAD measure for post sample data also, although they appear to be slightly different. Now that we have understood the computation of range and dispersion measures, let us focus on visualization of this sample. First, we'll start by plotting the density plot of pre-measure. For that, we'll again use the plot command on density of pre-variable. We'll add the main heading, central heading as density graph. The x-axis label, x lab argument can be set as data. We can use red color, call argument can be set as red. Also, we can set the line width argument LWDS4. As seen earlier, we can also describe the x-axis limits as 2 to 7, and we can also set the y-axis limit with ylim argument as 0 to 0.8. Now let us plot this data. We'll do an interesting exercise now. We'll try to superimpose a random normal distribution which has the same mean and standard deviation as this pre-sample measure. Let us do that. So first and foremost, we generate a random normal sample. We'll name it norm underscore pre, and we'll generate it with the following command: rnorm. 1000 values we'll give to this sample, and a mean which is same as mean of pre-sample data, and the standard deviation which is also similar to standard deviation of pre-sample data. Now we have generated the sample. We'll plot the density of this sample with the lines command. We'll not draw a new plot. We'll use the lines command to draw the density of this plot on the same original old plot. We'll give it a color of green, and we'll set the line width as 4. Let's see how it appears. An interesting thing appears. We can see that the distribution, the density distribution of pre-sample data and a normal distribution with same mean and standard deviation are not similar. While they may appear to be symmetric to us, but their peak is quite different. The random normal distribution has theoretically well justified peak, while if you look at the pre-sample data, it appears to be bimodal. So there are two peaks. That means two set of observations have particularly large probability densities. With this, in a very similar manner, we'll also compare the density plot of post data with a random normal distribution which has the same mean and standard deviation as the post data. So as a first step, we'll plot the post data. Again, we'll use the same convention. We'll use the blue color. So we'll plot the post data. We'll generate a random normal variable with name as norm underscore post, which has the 1000 values, but mean and standard deviation same as post sample data. So we'll plot this or superimpose this normal distribution, which has a mean and standard deviation same as post sample data. We'll plot this. Notice again, both of them, the post sample data and random normal distribution, may appear similar in terms of their symmetry, but again their peaks are quite different. As expected, the random normal distribution has quite a nice peak as expected from theory, but the post sample data again appears to be slightly bimodal with two different peaks as it appears, and both of these set of observations appears to have quite high probability density, and it appeared to be sort of bimodal distribution, so not similar. But please remember our discussion about central limit theorem. Even though this post sample and pre sample data are not or do not conform exactly to normal distribution, but in large samples, repeated sampling, often it is argued that the statistics computed from the sample approaches, their mean value approaches to normal distribution, and therefore CLT, central limit theorem, allows us to do various statistical procedures with assumption of normality. Now let us superimpose the pre-sample and post-sample data with each other. We'll try to compare them. We'll compare pre-sample and post-sample data. We have 50 observations of these data. So first, as a first step, we'll plot the density of pre-variable again, like we did earlier. So we'll plot the, using the same command, we'll plot the density of pre-variable. Now we'll plot the, or we can say superimpose the density of post variable on the pre-variable. So as a first step, we are plotting the pre-sample, then post-sample, and then we can also add a legend to it. Legend can be easily added on the top left corner. Maybe we can decide the location as we may find suitable. We can again, as earlier, we can give the name post and pre to post and pre-sample data. We'll follow the earlier convention of color. We'll give the fill at blue and red for pre, blue for post. So we'll fix the colors and then we'll add the legend. Now again, notice both of these samples give a clear picture that there is a shift from pre to post due to training. Now this inference is quite similar as we draw that from our original data, or what we are calling as population. The inference from sample and population are quite same. That is, in the random sample, we clearly find that there is a shift in distribution. Interesting to note that without using all that 1000 observations from the original data, we are able to make the same inference with just 50 observation sample. With this, we have understood the random sampling. We'll also try to examine some of the other methods of sampling as we discussed earlier. Now that we have understood simple random sampling, we will start with other types of probability sampling, starting with systematic sampling. Systematic sampling. As part of systematic sampling, individuals are chosen at fixed intervals from the population data. For example, to create a sample of n from a population size p with fixed interval k, you have k equal to p by n. That means if you have population of 1000 and you want to create a sample of 50, you need to pick observations from every 20 observations sample. So your length of observations is 20 and you'll be able to choose 50 observations. Now, why would you do that? Many times, if you believe that your samples are coming from a fairly uniform observation, so that if you divide your observations in a certain intervals, let's say 20, 20, and you have 50 intervals, the samples that you will get from each of the 20 observations are not so different from each other and they fairly represent your population, then it will save a lot of time and resources while doing the sampling exercise. And you would be comfortable fixing a certain length. Now, fixing the length is a trade-off. If you increase the length of interval, you will get less observations in your sample. If you decrease the length, you will get a large number of sample, but again, the time and cost involved in sampling may be higher. So as a starting point, first we need to install a package called teaching sampling. So we'll install this package called teaching sampling. Once you install this package, you need to put this in your current working library. This package teaching sampling will put it under the current working lab directory. Now, the format, the syntax to implement is quite easy. We will use this variable syst underscore sample equal to s.sy. Will tell R that there are 1000 observations and we need to break it into 20 intervals. This will generate a vector of indices. This vector, if I want to check the length of this vector, a vector of indices has a length of 50, and inside this index vector we have locations. I repeat, we have locations starting from 1 to 1000. In between we have randomly chosen samples which indicate the location of variables. So if I want to select the location for pre-sample, let's say we select for pre-sample, the location is equal to, we can choose our variable data $pre and we can select the index variable as our location variable by putting it inside the subscripts for data pre variable. And we can generate a set of 50 observations which are systematically chosen observations for our pre variable. Similarly, I can select another set of 50 observations purely randomly chosen for our post variable as well. So I can again run the same set of codes for our post variable also, and we can generate our post variable. Now we can do all the statistical analysis that we have done for our random sampling exercise. We can repeat all the exercise again, but just for saving time we will not do that, but we'll simply only see the summary of our newly created pre and post samples. So just have a look at our newly created pre and post samples, and please notice there is a clear cut shift. Notice that there is a clear shift in our pre and post sample data, which suggests that indeed there is an impact of training on our pre and post sample. Now let us start with the stratified sampling. It is another part of probability samples. So we'll talk about stratified sampling. In stratified sampling, you want to create, or you already have some predefined strata in your data, and you do not want to ignore these strata. For example, you may have in your survey respondents male and female candidates, and you wouldn't want to miss the responses from one set of gender. For example, you would want to give certain equal weightage in your both of these strata of male and female respondents. So you would try to take a sizable component or sizable number from both of these strata. Let us do that for this particular example. So for that, we need to install dplyr package to implement the stratified sampling. We need to install dplyr package. Once it is installed, we'll add this dplyr package to our current working library. Now we'll simulate the gender variable where female equal to 1 and male equal to 0. In this way, we'll simulate the gender variable. For that, we can simply add a gender variable, a simulated variable, to our data. We'll define this as factor. Factor is a categorical variable in R. So the procedure to generate this simulated gender variable is quite simple. We'll run this runif command and generate 1000 values from 0 to 1, and we'll round them so that we have exactly 10 values. Since we have converted them into factors, their meaning as a numeric is lost. They are only factor to R now. So our gender variable is created. Once we have this gender variable, we can run a sample command by going inside the data variable. Inside data, we group it with group underscore by function, and we group according to their gender. Inside gender, we apply our sample command, and from each of the genders, we pick exactly 25 observations. This will help us giving equal representation to both male and female respondents, so that 25 are chosen from male and 25 are chosen from female gender. We'll run this command, and now we will extract the pre and post sample data. For example, with this command, we'll extract our pre sample data, and with sample $post, we'll extract our post sample data. Now again, we can repeat all the summary and visualization analysis that we have seen for our earlier samples, but just for the sake of it, we'll add summary measure for pre, and we'll also add the summary measure for post. We have given equal representation to both of our strata, that is male and female, and notice there's a clear cut shift from pre-sample to post-sample. So this is our stratified sampling. Now we'll talk about cluster sampling. In a cluster sampling approach, the population is first divided into small groups known as samples. Then randomly we choose a certain number of clusters, and then once you have chosen certain number of clusters, you probably choose observations inside each cluster. The business argument behind choosing clusters can be like this. For example, you may have different income segments in each department of your organization. Now, you wouldn't want to miss out on any particular income segment. Probably you would want to give equal representation to each income segment. So therefore, you cluster in each department, you create different income segments. Each department will have certain high income segment and certain low income segment. Now, you can select maybe from a large number of high income segment, you can select a certain high income segment. Again, repeat the same for low income segment. And again, if there is another category called mid income segment, you also pick a certain clusters from mid income segment. Now, from each of these clustered segments, you can sample data. This will save a lot of time and cost for your sampling exercise. You need not look at all the clusters. You can probably from homogeneous clusters pick and choose a smaller number of clusters. So this is the kind of business situation where clustering exercise or cluster sampling would help. How to implement that in R? So for that, we need to install a package called sampling. Once this package is installed, we need to add this package to our current working library. Now that this sampling library is added, we will first and foremost generate a sequence of department, a simulated number from 1 to 50 for all the 1000 observations. So we are adding a sequence and defining it as a factor because it is representing a department. So each number corresponds to a department. It doesn't have exactly a numeric meaning. It's more of a categorical variable. So we are generating a sequence of 1000 numbers, randomly assigning numbers from 1 to 50. Each number from 1 to 50 represent one of the 50 departments. So once we have generated, you can see also, so this will be a sequence of 1000 numbers, categorical values starting from 1 to 50. These are departments for us. Now we'll do our clustering exercise. So we'll assign these clusters to a new variable called sample, wherein we'll run our cluster command on our data variable called data. We'll give a cluster name equal to department. So a cluster of departments will be created. Now we'll give a size of 10. That means out of 50, only 10 departments will be chosen. Probably our belief system suggests that all these 50 departments, 10 departments are fairly representative. So also we are using a technique called simple random sampling without replacement, RSWR, for our clustering procedure. The idea is that the probability of each of the cluster of being selected is same. So there's no, it is without replacement. So now let us see the dimension of this cluster variable. Let's see the dimension of this data sample. We have created this data sample. Now let's find the dimension of this data sample. It is around 216. We can also see what are these departments that are selected for our exercise. So we can see that we can add this levels command, and once we add this levels command to our data sample $department, notice that it shows me all the 50 departments. However, we have asked the command to select only 10 samples. The problem here is that as the way R works, it keeps, or the original cluster of original departments are still stuck to the variable. So how do we remove this? We add a very simple command called drop levels on our original data. So we'll add drop levels command and drop these unused levels from my data. Once you do that, those levels are dropped, and now when you run the levels command, notice only 10 levels are appearing. These are the representative levels that are chosen. Once we have selected the levels or departments, the 10 departments, we can very well select a certain number of observations to get our final sample. So we'll name it final sample, which is equal to data underscore sample. So we are selecting the data from our original sample with 10 departments, and we are grouping it by department only. Inside departments, from each department, we are using the techniques of sampling, and from each department we are picking only a size of 5 samples. So now this final sample, let's see the dimension of this final sample. So there are only 50 observations as we would have wanted. Now let's say select the pre-sample variables from this final sample. Let's select that. And we'll extract the pre-variable first. So we'll extract the data. We'll use this get data command, and from the original data, which is my data variable, I'll extract this final sample and we'll name it new data. From this new data, we'll extract the pre-variable, which is of importance to us. Pre-variable, we'll assign it. Similarly, we'll extract our post variable also from this new sample. While other visualization and summary analysis remains the same as for the random sampling that we did, let's only look at the summary variable for our new pre-variable obtained using cluster sampling. And also we'll do the same for our post variables. Again, please notice, as we have seen earlier as well, there's a clear-cut shift in the pre-sample and post-sample values, indicating that there is indeed a significant impact of training and development exercise on employee satisfaction. Now that we have seen various approaches to sampling the data, let us start with confidence interval estimation. We'll explain and implement confidence interval estimations for our pre and post survey response data. For this, we'll use normal distribution with Z statistics and students T distribution with T statistics. We'll discuss the implementation in a detailed manner to explain the concept and also see the QUIP implementation as well. We'll compare the T and Z values and also the resulting confidence intervals. We'll try to describe and explain the differences between both of these distributions and the implication for analysis. We'll also simulate normal distribution and students T distribution to understand the difference and its implications for confidence interval analysis. Next, we'll also discuss a case of binary distribution. We'll discuss a business case wherein the organization focuses only on certain individuals with a score of less than 4.5 as detractors and more than 4.5 as promoters. The organization wants to focus their training and development programs on these detractors with a score of less than 4.5. Therefore, it assigns a value of 0 to these detractors and 1 to promoters. Given the binary nature of data, that is 0-1 categories, it needs to be modeled using binomial distribution, and using confidence interval estimation, we need to assess whether the data fairly describes the original data with 1000 observations. We'll also try to make some inferences about the impact of training and development pre and post sample data, and further make inferences about this impact on population. Now that we have understood various sampling techniques, we'll employ them in our confidence interval estimation, and we'll understand this process of confidence interval estimation and its application with R. So we'll start with confidence interval estimation. When we wanted to estimate the population parameter, let us say population mean, we can employ sample estimator, for example, sample mean. In fact, if you want to estimate any population parameter, you can use sample statistic. So in this fashion, you define confidence interval as an interval surrounding the parameter, and the interval has a certain chance of being the true statement or definition of being the population parameter. So how do we interpret this confidence interval? The statistical interpretation is quite simple. It is the confidence interval. It has a certain probability 1 minus alpha, where alpha is the critical value or the complement to the confidence level. This probability of containing the population parameter. For example, if you have 95% confidence interval, which falls between 0.65 to 0.73, then you would say that there is a 95% chance that the interval of 0.65 to 0.73 will contain the true population parameter. Now we'll perform this exercise on our pre and post sample data, and we'll do this in a step-by-step manner. Please note there are certain differences between t distribution and z distribution. We'll use these t statistics and z statistics in our interval estimation. There's a fundamental difference between these two distributions. The t distribution depends upon the degrees of freedom, as we have discussed, and curves with more degrees of freedom are taller and have thinner tails. T distributions have heavier tails than the z distribution. So that means it needs more evidence, or heavier values of t are required for same level of confidence interval estimates. So let us start with our interval estimation process, and first we'll install the relevant packages. In this case it is distributions 3. This is our relevant package. We'll install this package, and once we have installed this package, we'll use library command to put this package in our current working directory, library. Now first we'll start with the z-test statistics. Although z-test statistic is less practical, as we have discussed, t-statistics is employed when either you do not know the population standard deviation, or in cases where you have less sample values, for example 30, 40, 50 values in your sample. In those cases you prefer to use t-statistic, which is more efficient in these cases. So but first we'll start with z-test statistic in confidence interval estimation. What we'll do is we'll try to estimate some population parameter like population mean using the sample estimates, conduct the confidence interval estimation, and see whether actual population parameter is falling in that interval or not. That will give us some idea about the efficiency and effectiveness of the sampling process. So in our case, we have already taken the sample from our random sampling process. The sample mean is 4.05, but this is just a sample estimate. We need to generate the confidence interval to say that actual true population parameter lies in that interval. So let us decide our confidence interval as 95%. So our complement value or critical value is 0.05, that is 5%, and therefore obviously our confidence interval is 95%, as you can see. Next, we need to generate a normal distribution. Since it is z statistic based confidence interval estimation, we need to have a normal distribution. In fact, we need standard normal distribution which has a mean of 0 and standard deviation of 1. So now that we have generated this normal distribution, let us look at some of the parameters. So if you want to check the mean of this normal distribution, it is 0. The standard deviation of this normal distribution is 1. In fact, we can see the plot and also make out some inferences about its characteristics. So when I plot this, it clearly appears as a very normal, smooth, stable, normal, standard normal distribution. As a second parameter, we also need the standard error of the estimate. So standard error of the estimate in case of Z statistics, it is standard deviation of the population, which would be data $p. Since in this case, the 1000 observations are used to generate the small sample of 50 observations, we will consider this original data as population only. So its standard deviation is employed in computation of standard error divided by the square root of sample size. So sample size in this case is 50, which can be easily computed as length pre. So now we have our standard error of the estimate, which is around 0.08. Next, we also need to compute the value of Z statistic. Z statistic can be very easily computed with the help of quantile command. I can generate the relevant quantile for our normal distribution, which we have just generated, and specify the confidence interval, that is 1 minus a by 2. Why 1 minus a by 2 we are using? Because we are saying it is a two-tailed test. That means the actual population parameter can move either on the upside or on the lower side, both positive and negative side. So we are considering both tails, and therefore we are using 1 minus alpha by 2. That means starting from 2.5 percentile to 97.5 percentile, since our confidence interval is 95 percentile. So that means this 1 minus alpha by 2 will represent 2.5% to 97.5% interval, which is essentially 95% only. Now we have computed our Z value in this fashion. Let us compute our margin of error MOE. Margin of error equal to Z statistic into standard error. Now we are done. We need to compute the lower limit of our confidence interval, very easily computed as mean, which is our sample estimate of mean, minus margin of error. Similarly, I can compute the upper value of the confidence interval, very easily computed, mean of sample plus the margin of error. So if I compute these values, let us have a look at these values. So the lower value is 3.90, rounding off, and the upper value is very easily can be seen here, 4.21. So this is my confidence interval of 95%, where I'm estimating that in this interval I have 95% confidence that my true population parameter should lie. Let us look at the true population parameter value. In this case, we are saying that original data is data itself, and we are assuming it to be our population. I can simply compute its mean as 4.00. So it appears indeed this population parameter falls inside that 95% confidence interval. So our sample is reasonably good. Now, as you keep on increasing the level of confidence, you increase the sample size and decrease the alpha value. There's a trade-off. The more confident you want to be, you can increase the confidence interval, but at the same time, there's a cost in terms of efficiency. So either you increase the confidence interval and decrease the alpha value, or you increase the alpha value and decrease your confidence interval. So with this, we have been able to compute the interval estimation using Z statistic. Now, in the next video, we'll talk about confidence interval estimation using T statistic. In this video, we'll perform confidence interval estimation using T statistic. So we'll have confidence interval estimation using T statistic. T statistics are defined by their degrees of freedom corresponding to the sample. So first we need to compute the degrees of freedom, which can be very easily computed with this length command. I can compute the length of my pre-sample, which we have been working on. And this DOF is my degrees of freedom. So I assign the value of degrees of freedom to my DOF variable. Next, I need to compute the T statistics, which is quite easy. I can use this T equal to QT function. QT function is basically to generate the quantiles from T distribution. So I will use this, and my critical value I'll define as alpha by 2 because it is a two-tailed test. So as we discussed earlier, we are using alpha by 2. Then I assign DOF, degrees of freedom, to my DF variable, DF equal to DOF, and I specify that lower dot tail equal to F. If I do not do that, it will give me other tail. For example, if it is a 95% confidence interval, if I put a lower dot tail as true, it will give me 2.5 percentile value. If I put it as false, it will give me 97.5. So both cases are fine, but in this case, I'm using lower dot tail equal to false. As a next step, I'll compute standard error of the estimate. Next set of steps are quite similar to what we have done earlier. So standard error equal to standard deviation of pre. Please notice that in the previous case, we were using the population standard deviation, but as per the assumptions of T statistics, we already know the variation of the population in case of Z statistic, but in case of T statistic, it is assumed that samples are small and generally we do not know the variation or standard deviation of our population. So with this, I divide it by square root of length of pre-variable, and in this fashion I compute my standard error of the estimate. Next, I compute margin of error as done earlier. Margin of error is T into SC, which is my standard error. So I get my margin of error. Then using this margin of error, I can compute the lower bound of my confidence interval, which is mean pre minus MOE, and I can compute the upper band as well. So we can see this confidence interval easily. So lower is 3.88 and upper is 4.23. Now, if I want to confirm whether my true population parameter, which is the mean of the sample, that not the sample but the actual data, original data itself, that is data dollar pre, let us see that. So my mean of original data is 4.00, which actually falls in this confidence interval. That means my confidence interval, where I said that 95 with 95% of probability, I assume that my true population parameter should be lying in this range, which is true, it seems. But please also remember that when we computed this exercise through Z statistic, then also we successfully found that our true population parameter lied on the same confidence interval using Z statistic as well. And therefore, what was the need to conduct this exercise using T statistic? And for that, please have a look at T and Z values computed in this exercise. T value is 2.0 and Z value is 1.96. This is a clear indication that for same level of confidence, for me to have the same level of confidence, I need a relatively higher evidence. I need a higher T value to generate the same level of confidence. To talk about more on this, let us try to visualize. What is happening here. So we'll plot the density plot of the normal distribution using rnorm command, and we'll generate, let's say, 50, maybe 100 values. I'll assign a color of red, line width of maybe 2, and we'll not assign any central heading here. That we'll do in legends. We'll add legends to make it more clear. The plot is provided on the plot window, and now I'm adding the T statistics also, and for that I need to use RT command, which will generate the density distribution for a T distribution with 500 observations and df equal to, let's put df as equal to 20. Again, I'll use the same argument color. I'll put to green, and remaining arguments remain the same. So when I generate this graph, please notice the T statistics is very clearly very different from this one, the red one. Let me add legends also to make it more clear. So I'll add legend also, the legend to be added on top left side. I'll give the name as T distribution and normal. I'll also follow the same convention by providing the fill as equal to green for T distribution and red for normal distribution. So now you have the commands, and now I can run this command. So I have my legends also. Now please notice, as of now, the T distribution is quite different from the normal. In fact, it deviates a lot. Notice, I'll zoom it. Notice the tails of this T distribution. The tails are much fatter. While its peak is lower, the tails are fatter, which indicates that for a T distribution, it has higher probability of finding observations on rather extreme tails and a lower probability at closer to mean. That means its mean and mode are smaller, which suggests that the most frequent observations that are closer to mean or other measures of central tendency like median, mode, is much lower and more observations are spread much further away from these measures of central tendency. With this understanding, let's change some of these values. Let's generate slightly higher values. As you can see, as I increase sample size, both of these distributions, they become closer to each other. For example, if I put, let's say 5,000 observations and increase my degrees of freedom to 200, very large number of observations, they almost appear identical, which means when I have large number of values, whether I do it with Z statistic or with T statistic, the interval estimation process is almost similar. But if I have less number of observations, let's say 100, and very low degrees of freedom, let's say 10, and if I run this, notice the plots deviate a lot. The tails are much fatter and the peak is much lower, and therefore in this case it will be better to perform this interval estimation with the help of T statistic. So this is the reason we use T statistic when we have small number of values. Also, there are some shortcut ways to conduct this T test statistic related interval estimation. We can simply use this T dot test on my pre variable, and notice on the console window you notice the confidence interval, which is same as we obtained using the detailed procedure where we manually computed the interval. Another shortcut to do this is from linear regression models. So I run this conf int command on my lm mod command. Lm is basically for linear model or regression model. So I can regress my pre variable on a constant term, that is 1, and generate the confidence interval for the constant estimates. Please notice the estimates are identical as our earlier confidence interval, which is 3.88 and 4.23. So it is another trick to estimate the confidence interval for the sample, or you can use directly T dot test. So with this, we realize what is the importance of conducting t-test with small samples. And in the same fashion, we can also conduct confidence interval estimation for our post sample variable as well to see the effectiveness of our sampling exercise. With the sample estimates, we can check and compare them, and their confidence interval we can construct and check if the population parameter is falling in those confidence intervals, and therefore how effective our sample is. In this video, we'll model the data with the help of binomial distribution. We'll conduct confidence interval estimation and make inferences about the population parameter and also the impact of training and development on the employee satisfaction. So we are analyzing binomial distribution and generating confidence intervals. The binomial distribution model deals with finding the probability of success of an event which has only two possible outcomes in a series of experiments, that is success and failure. The business case for our exercise is as follows. The organization wants to specifically focus on those individuals that score low on satisfaction and wants to design training and development programs that are more suited and customized to their needs. So an individual below a score of 4.5 will be assigned a value of 0 and is considered as detector, while those above 4.5 will be assigned a value of 1 and are considered as promoters. So as a starting point, let us examine the pre-sample data. So for that, we'll create a pre-bino variable. This variable will be added to the pre-sample data. So we ascribe to a pre-sample a value of 0 if it is less than 4.5 through this command, and a value of 1 if it is more than 4.5, and this pre-bino variable will be added to those employee codes. Let us have a look at the sum of this variable pre-bino. So this variable suggests that there are 17 employees in our sample that have received a score of 4.5, and therefore this pre-bino variable is 1, more than 4.5, and remaining score of 0. So if I want to know the fraction of those that have scored 1, I can simply divide this summation by the length of pre, which is 50. This means that 34% of the employees in this sample are satisfied. Now you may want to check the confidence interval, that is maybe 95% confidence interval, in which you believe your population parameter will be there. So for that, a simple command prop.test we can apply, and we can define the sum. So this will give us the number of occurrences, which is 17. 17 times we have employees that are satisfied, and the total length of sample we'll put the formula, although length is 50, but still we'll use this formula to define the length. Then we'll put the confidence level as 95%. If I run this command, notice the confidence interval estimate of the population parameter. It is from 0.215 to 0.488. And the sample estimate, as we already know, 0.34, which is 17 upon 50. Now you would like to know how efficient is this estimate, how correctly it defines the reality. So in our case, first we need to know how many times in our population parameter the value is more than 4.5 or less than that. So for that, again, we'll perform the same procedure, but this time we'll use the population. We are calling our 1000 observation data as population in this case. So let us use that, from which actually the random sample was taken. If it is less than 0.5, then we take a value of 0. If it is more than 0.5, we take a value of 1. So this is our population parameter pre-training. Now we can compute the summation, that is those who are satisfied, with this simple command population pre, and we'll divide it by length. So it is quite simple. With this, let us see the number. So it is 25.5%, which is slightly different from the sample, but it is still falls in that 95% confidence interval. That means our sample fairly accurately describes the reality, and it suggests that the original population parameter falls within the range of 21.5% and 48.85%, which actually is true. So our sample is a fair representation of reality. Now with this, in the next video, we'll talk about the post sample, its properties, and whether it is able to provide that confidence interval for population estimate, and we'll also compare the impact of training and development on pre and post samples. Now we'll examine our post sample data with the help of binomial distribution and conduct confidence intervals. So we'll examine the post sample data with binomial distribution and confidence intervals. So first, as we did earlier, we'll generate this post bino data, and here in our sample, those values that are less than 4.5, we'll assign a 0 for those values and 1 for those values that are more than 4.5. We'll assign these values. Now if I want to know how many individuals this value was 1, I can check this summation post bino. It seems this number is 39. It has increased significantly. I'll divide it with the length of our sample, which is length of post, and notice the fraction. This is 78% is our sample estimate. So this is our sample estimate for getting a value of 1, that is response of more than 4.5. Now you would like to generate the confidence interval for your population estimate, and as we did earlier, we'll use this prop.test sum post bino, which will give us the number of values that are more than 4.5, and then sample size. This is post, and we'll assign a confidence level of 95%. So when I conduct this confidence interval estimation, please have a look at this confidence interval of the population estimate, which is 0.64 to 0.88, and the sample estimate is 0.78, which was expected, as we already saw. Now to check the efficiency of this sample, or the ability of sample to correctly define and describe the population parameters, let us compute the population estimate, and for that I need to generate the values of zeros and 1. Again, same procedure. For data dollar post, in this case data variable original 1000 survey responses acts as our population data, because from this data only we have generated the sample estimates. So if this is less than 4.5, we will assign a value of 0, and if it is more than 4.5, we'll assign a value of 1. Let us compute the values, and now we'll see what is the total fraction of the population post divided by the length of the sample, which is the length of population, which is 0.75. So the sample estimate is 0.78 while the population estimate is 0.75, which is fairly closer, and also this number falls well within this 95% confidence interval. So first we got an idea that our samples are fairly describing the population, but more importantly, have a look at the confidence interval estimate before and after, that is pre and post. So before, the estimate is 0.21 to 0.488. So this is our estimate before training. After training, our estimate is 0.64 to 0.88, which clearly indicates that there is a shift in the employee satisfaction. So pre-survey sample data and post-survey sample data clearly indicate that there is a shift and there is a significant impact of training on employee satisfaction. That means there are much more employees that are satisfied with a score of 4.5, more than that. That is one very important inference that we can draw from this analysis. And therefore, it seems that our training and development program is successful. So this is how we tested. We modeled the data, sample data, using binomial distribution, and we conducted the confidence interval analysis and also saw whether our sample properly describes the original population data, and it also successfully indicated the impact of training and development program on the entire population.